Okay, so in this example, we're going to look at another particular relation. So we're going to start with our sample set A, and it's going to be a little bit bigger than our last one. 2, 3, 4, 5, 6, 7, 8. So all of our members. And we're going to define our relation as, again, between x and y, for x is not equal to y, and 3 divides x minus y. Okay. So, as with before, our first step is going to be figuring out all of the members of this particular relation and writing them out explicitly. So, starting from this, we can see that 2 and 2 is not going to be in our relation because we've got x is not equal to y. And in fact, the first number that I can come up with, at any rate, the first set that does hold true for this is 2 and 5. So we've got x is not equal to y, but we've got 2 minus 5 gives us minus 3, and 3 does divide minus 3. Okay. Now, the reverse of that is also true. So if we've got 5 and 2, so they're not equal, and we've got 5 minus 2 is positive 3. 3 divides itself, therefore that holds true. So you kind of can see the pattern from here. So let me go ahead and fill in the rest of the examples here. So 2 and 8. 8 and 2. Continuing on. 3 and 6. And 6 and 3. 4 and 7. 7 and 4. And 5 and 8. And 8 and 5. Okay, so I think that is all of the members of this relation for this particular set we're mapping from and to. I did this myself, so if you see any errors, do let me know in the comments or flick me an email, because I'm not perfect. I will screw up things. But now we've got our basic set of relations, we can test those 4 things we did in the previous video. So we can test whether it's reflexive. So again, just remembering with reflexive, you're asking if x maps to itself. So if your first number maps to your first number again. And so we can see immediately this relation is not reflexive because we don't have any examples where 2 is mapped to 2, 3 is mapped to 3, 4 is mapped to 4. And in fact, this relation expressly forbids it being reflexive. So it's definitely not a reflexive relation. And next one, symmetric. So just a reminder, your symmetric is you're testing if for all the examples of x mapped to y, y also maps back to x. And remember here, we're looking for single counterexamples. It's much harder to show that all of the things that are there are true, rather than just finding one example where it's not. But here we can see our first example, 2 to 5, is then mapped straight back 5 to 2, which is symmetric. Is it true for the next one? 2 to 8, 8 to 2, yes. 3 to 6, 6 to 3, yes. 4 to 7, 7 to 4, yes. 5 to 8, and 8 to 5, yes. So that means all of these elements are symmetric, and therefore this is a symmetric relation. Moving on now, we'll check whether it's transitive. And this is checking if x maps to y and y maps to z, then z must also, x must also map to z. So it's just saying if we had, say, 2 to 5 and 5 to 10, then 2 should also map to 10. Now, what we've got here is kind of an interesting case because we don't have any examples where x is mapped to y and then y is mapped onto something else. So we don't have anything mapping from 5 to anything. We don't have anything mapping from 6. Oh yes, we do. So we have 2 to 5 and then 5 to 8. So for this to be transitive, we must also include the relation 2 to 8, which we do. And now in reverse, if we go from 8 to 5 and 5 to 2, we also include the relation of 8 to 2. All right. So this is, in fact, a transitive relation, because we can't find any counterexamples where this does not hold true. Our final test is anti-symmetric. And again, we're looking for counterexamples. So our anti-symmetric relation is if x maps to y, y maps to x, then x is equal to y. And looking at our very first example, because 2 maps to 5 and 5 maps to 2, and 2 is not equal to 5, therefore this is not an anti-symmetric relation. So it's symmetric and transitive, not reflexive, and not anti-symmetric.